Uh, Today we are going to discuss about the IV of MESFET. So just remember our threshold voltage characterization or threshold voltage definitions, which we had last time, and couple of things that we had a discussion. And the important part here, if you can notice, just try to see like there are two types of pinch of voltage you may encounter. One is actually like if you are okay, just let me draw so that you won't have any difficulties to understand. Okay, you have a source which is ohmic contact or low contact resistance part. You have a drain, sorry, we have a gate, which we, let me plot it in this manner. We have a source and we have a drain. Right. We have a source, we have a gate, we have a drain, right? And this is actually, I have mentioned, it's a semi-insulating semiconductor. Okay. Why it is semiconductor? As I promised you, I'll discuss that matter later, not now, because we are discussing about the basic properties of MESFET. MESFET means metal semiconductor field effect transistor, right? So in this case, here also I have mentioned, if you remember correctly, that it is actually N-type semiconductor. Okay. And here also I didn't mention anything about type of semiconductor. Like I didn't say that whether it's a gallium arsenide, gallium nitride, or silicon or germanium. Yeah, I didn't say anything about. You just recognize, you just consider it is as a N-type semiconductor. In this situation, what happened? You might have two type of uh, like pinch of voltage. So one is, just refer our last discussion, VBI minus B threshold. Another one is actually VP0 is actually VBI minus VGS plus VDS. Just go back and check. Okay, I think during the discussion, yeah, this is actually. And we are mentioning is actually VD sat means saturation voltage, right? Two type of. Here, don't confuse about this is actually, right, if you want to close your junction by applying gate voltage. So it is very important, like if you want to close this junction by gate voltage, and if here actually if you want to close this junction by drain voltage, right? But what happen, you cannot really close this junction, and that discussion we had last time, right? So this is very important to understand. Now, but the problem is that this phenomenon, like always, but like if you have a MESFET and you always try to operate this MESFET by applying gate voltage and by applying drain voltage. So there is no actually particular situation, not as a special situation. There is some special situation that you always want to apply gate voltage without applying any drain to source voltage. But if you consider our IV characteristics, so IV characteristics means, like if you can remember our IV characteristics, right? And this is actually VG S is equal to 0, right? So like you are applying always a drain to source voltage. If you apply and it is ID, right? You have a drain current, you have a drain to source voltage, right? So now remember the situation is that you are applying gate to source voltage, you are applying drain to source voltage, everything you are applying. See in this condition, how my current, right? How to calculate my current through this transistor. That is the important part that we need to consider over here. Now let's draw this part. So what is the thickness from here to here? You know, we already have done it, and we are mentioning it is A. And suppose this is my gate voltage. Sorry, this is my depletion region, and this is my H. But let me write it Hx. So X is variable because why it is variable? So like, you know, you have a H. So I'm saying that this is okay. So H, this is Y. I'm writing HY, right? So you see that this is my Y direction. Current is flowing my X direction, right? And my H is a function of Y, means like here my H is totally different than when H is changing. Source side H height and drain side height is totally different. It's a function of Y. So that is actually variable. That's what I'm writing over here. HY, right? Now what we have to do, I need to calculate the current, right? So let us see that I take a piece, right? And so all these things. So and we know that what is the current, and you have applied, and here actually voltage is suppose very small voltage, it is dV, right? And you see like this side it is drain to source, this side it is drain to source, so VDS you are applying, and this side it is it is VS, this is, and this is actually, this side is actually VDS, right? So I should VDS, VSS and VDS, right? So, right. So this is the voltage you are applying, okay? And here also you consider that my source is connected to the ground potential. My source is consider is ground potential, right? So that makes a zero potential. Okay, so let us try to draw the part. You know how to do it. So you know V is equal to IR. That's very common. V is equal to IR. Okay, so let me write dV. I can write I, because current is constant. Whatever the zone, you can see that current is linear, no? So current is constant. So you cannot like R is equal to rho. Okay, and you can write dx L by A. A means weight, right? And you know how the current is flowing? Current is flowing between here to here. So current is flowing between the open portion over here. And what is this like zone? H, A minus HX, A minus HY. Through the H, A minus HY, my current is flowing. So, and transistor is not like a 2-dimension, it is having some width. So that is actually width, and my effective A minus right. This is the my things. So this is my expression. So that expression come from this simple rules, V is equal to IR, Ohm's law. From there, I just drive it, right? Now, let us see, like, what is the current? So current into I into dx, okay, into dv. Please help me if I'm doing any mistake. dv into A minus hy, right? dv. So, but I have a w I dx. I w dv A minus hy into w dv. What would be the rho? Okay. Mm. So, okay, I into dx, right? So you can write w, rho means whatever, rho, and then A minus hy. No, sorry, somewhere dv is there. So limiting factor, like boundary condition over here. So let us draw the boundary condition. So we are actually trying to calculate the current from, so this is my, so this suppose is my L. L is the means length. Okay, so we are trying to calculate the current at L. So source side L is equal to source side L, so coordinate is 0 at source side, so I'm writing source, and it is L, I'm writing at drain side. Similarly, we should have, so now source side, what is the voltage? Vs and VSS, and it is VDS. Correct. Or now you do perfect integration. So I W L. So this is resistivity. So I can write conductivity if you wish. Okay. Then actually now you see there's a problem. Like, what is the problem? What we are facing? Like, we have a voltage limit, VSS. No, okay, we have a voltage limit, and VSS, what I said, my source is ground. My source is ground. So VSS, my 0 voltage, and it is VDS. So no issue. But you see, I have a voltage limit, but right side, I mean, like, all this part is nothing but my length, right? So I have to convert this length part into voltage part. For an example, like what I'm trying to see, like, okay, that will be clear in a minute. Like A is a length, 1 minus hy, okay, dv. What I'm trying to say that we have a voltage limit, boundary condition, but we have the factors in terms of length. So we have to convert these things as a variables with voltage. So what we have to do? Okay, let's take A out. The moment you take A out, W, rho into L. What is that? This is actually conductance. So this A W rho by L, this is nothing but conductance, opposite of resistance, right? Okay, and now we have to find out Hy. What is my? We have to find out Hy by A, okay, in terms of voltage, so that we can, in terms of voltage, then only we can actually put in this boundary condition, right? Now, what is H? But first of all, tell me what is A. Go back and check your last day discussion. I hope we have discussion on it. Okay, so if and just try to see that, okay, let's not disturb. What is A? Now you see that if you have a depletion region, so go back in your PN junction concept on how to find out A or like XT. What is the formula? You can remember the formula that what we have. Hello? Yes, yes, tell me. Yes, yes. Yes, yes. Yeah. Yes. Yes, yes. No, 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 no. There are only few things are asset, few things are consumables. Okay, I will ask one of my students to contact you and he will give you the details. So what is your name, ma'am? Hello? Oh, Lakshmi. Okay, I'll ask Krishna to call you back. Okay. So what is, so you remember your formula for depletion region. Can you remember your formula for depletion region? You can remember like this is actually 2 epsilon, right? VBI into Q into doping, if you can remember, right? So same way we can write here like 2 epsilon, but here VBI. But remember, here what is the VBI? Like I can represent VBI, a pinch of voltage. Suppose when we achieve pinch of voltage, it means when we achieve pinch of voltage, it means we close the whole channel, right? So that means this we can write in pinch of voltage, and that is nothing but Vp0, right? Into Qna. Similarly, Hx. So Hy, right? Hy you can see same way 2 epsilon. Here we have to write not pinch of voltage, because in this case we are trying to find out Hy voltage, that Hy distance with a function of voltage, right? And what is the voltage across Hy? That we can write in this manner: Vbi minus Vgs and the voltage anyway, Vy, all right? Because we don't know if my Vy, so remember this part, Vy is equal to Vd set at X is equal to L means, sorry, yeah, X is equal to L means when you are actually very close to the drain to source voltage, when you are very close to drain to source voltage, that time you are actually you have achieved the VD set. Very close. Otherwise, it is like that. Okay. So I mean to say, at the source end, your voltage is 0. At the drain end, your voltage is VD sat. In between, whatever voltage is there, it is nothing but Vy. Okay, that's what. No, Vy, we have to write Vx actually. Because the voltage across, yeah, not Vy. Sorry, it is Vx. Right? Voltage across X. Right? So you see the beauty of this thing, we have converted it into voltage part. Now we have to write Hy by A. So what is my Hy by A? You can write Hy by A. Vbi minus Vgs plus Vx into Vp0 under root. This is actually Hy by A. So in this case, what we have to do, now we are actually, now this value we can put it over here, 0 to Vds 1 minus Ebi minus Vgs plus Vx Vp0, but unfortunately this is having half, right, into dV. Okay, so we can write that final expression in this form. So I, we have a formulated by G. Then help me. It's a simple integration. You please try to do it. So I'm requesting you to try to do the simple integration and give me the answer. Just try to do it. Do it. This is the same expression we have handled. You can remember, we have handled last time when we have calculated the IV characteristic MOSFET. This is also same thing, 3/2 power law expression. Try to do it. Try to do this integration and give me the answer. So help me if I am doing any mistakes. VDS, then 0 to 1 minus, so it is a VDS minus, okay, minus VPI minus, okay, so minus 2/3 Vp0 . VBI GS plus upper limit, so VDS whole to the power 3/2 minus this is the expression that you are going to get once you integrate it nicely, properly, and without any error. So, but important part, just to verify it, cross verify that after integration you are getting it or not. But I think it is correct. What is important, if you just recall your discussion about the IV characteristics of MOSFET, and you'll see that this is the same laws, same rules, 3/2 power laws. We are all, that time also we got the 3/2 power laws. Here also we get a 3/2 power law for your current, right? This is the same thing, we got it. Okay. Now, what else? What you have to do here, you can, so this is actually general rules for the IV characteristics, and now we have to find out IV characteristics in linear mode, linear zone. So which is your work, which I am not going to do. What is the linear zones? Linear zones means VBI minus VGS greater than VDS. Right? You understand this part? So if you go back, okay, let me draw it here itself instead of going back. So if it is a linear mode, linear zones means like this zone, IV characteristics and these zones. And here, what I'm saying that in this case, your drain to source voltage VDS is less than VBI minus VGS. This is your homework, and you please try to calculate this part. There is no issue, absolutely no issue on it. What I'm going to do it, the other part, saturation. Two part is actually IV characteristics into saturation. Okay. So what is means saturations? So when VD set is, when you get a VD set like VDS or is equal to V X, okay, and it is actually VD set. Okay, so this is the zone where like when you have achieved VDS, VD set, and that time we are trying to calculate this part, right? Couple of things. So you know our formula for VBI minus V threshold is equal to VD set, VP0, and our things VBI minus VGS plus VD set is equal to VP0. We had this discussion last time, right? Now, so what is VD set? VP0 minus VBI plus VG set, right? Okay, so let us, so then you please modify this expression in this manner. It was a third bracket. So you are having VDS, but right, you see like, you see our original expression, it is actually VDS, but now we are trying to calculate the IV characteristic at saturation level. So it has to be VD sat, right? Minus, so let me write it is minus 2/3 of VP0, right? Minus 2/3 of VP0. This is the second bracket, and I think VP0 minus half, I guess, VBI minus VGS plus VDS simple, very simple mathematical manipulation. I is equal to C VD sat minus 2/3 of VP0. You know, this part, just carefully observe. VBI minus VBI minus VD sat, what is that? VP0, right? Our first, yeah, this expression. VBI minus VGS plus VD sat is nothing but VP0. So which we have to put. So we write VP0 whole to the power 3/2 minus what is VBI minus VGS? What is VBI minus VGS? So look at that. So here actually I can write VBI is equal to VP0 plus V threshold voltage. Okay? So VP0 plus V threshold voltage, right? So we can write the same thing. V threshold plus VP0 minus VGS whole to the power 3/2. It is that. Okay, what is VD sat? VD sat is VP0 minus VBI plus VGS, right? So let me write. So VP0 minus VBI plus VGS. VP0 minus VP0 minus VBI 2/3 of VP0. So 2/3 is equal to half. And here is the VP0. So if you take VP0 common, so you'll get a VP0 out, right? 1 minus VP0. So let me write 1 minus VP0. Okay, I write VGS minus V threshold voltage. So minus VGS minus threshold voltage minus VP0. Please help me if I do any mistake. So it is actually G. So VP0 minus VBI is nothing but threshold voltage. So VGS minus V threshold voltage, right? 2/3 of Vp0, 1 minus VGS. Three by 2, you have missed. So let me write one thing, VGS minus threshold is equal to VGS bar. So this is how the Shockley has drive. So that's what I'm writing also. VGS bar 2/3 of Vp0, 1 minus VGS bar Vp0. There might be some mistake. VPI plus VT set. That is also VPI minus VGS. So what is VPI? VPI, I'm just cross verifying VP0 plus V threshold voltage. So VPI plus V threshold voltage. VPI, VPI. V threshold plus VP0 minus VGS. Okay, so I can write VGS minus VGS VP0. So minus plus minus. Okay, so there is a mistake. I think you have noticed it. Minus plus, it is minus. It should be plus. Please forward. Please check it. Yeah. Please check it. Okay. Now it is, I think, looks okay. I think I can tackle it. 3 by 2. G VGS bar minus 2/3 of Vp0, 1 minus 1 plus VGS bar Vp0 whole to the power 3 by 2. G VGS bar 2/3 of Vp0, 1 minus 1 plus 3 by 2 VGS bar for Vp0. Okay, plus 3 by 8 VGS bar to Vp0. Okay. Just check it. So this is actually the what I have done. 1 by x is equal to n, 1 plus nx. But I have taken second. order actually, right? Same part. Now please help me to find out. So you can find out G. So this one, so it's nothing but mathematical manipulation. This one and this one get cancelled. This 3 by 2 and 2 by 3 VP0 get cancelled. So all these things he actually is going to cancel one by one. Ultimately, you will be left. So what I was looking something, if you try to manipulate like once, like what I'm trying to say, like 2 by 2/3 of VP0, this 3 by this one actually get cancelled. This 3 by 2, 2 by 3 get cancelled. This VP0 get cancelled. All these things, if you try to do all these things together, if you try to see all these things together, put back the G expression, conductance expression, you will end up with an equation mu C W by 2L VGS minus V threshold whole square. So just try to do it, because now I think it is easy. What is important over here? So that means your final current expression will come mu C W by 12 VGS minus V threshold, which is exactly the IV characteristics of MOSFET. But here is the difference. What is the difference? If you want to get a higher current, like even if you try to get a GM over there, whatever the GM, higher current or higher GM, that is actually our main intention, like, because higher GM means more frequency, right? You need to have a high mobility, that we have concluded. So how to get a high mobility? I should get high mobility not by silicon, because I have another choice called gallium arsenide. So this mobility is nothing but gallium arsenide choice. Another fantastic thing has happened, and that is if you look at the structure. This structure is not at all surface device. What do you mean by surface device? Look at that IV characteristics of MOSFET. Your electrons is nothing but your current is flowing across the interface of silicon and silicon dioxide, right? So it is very prone, and the electron mobility across any surface, is reduced. Why? Because silicon dioxide interface or silicon or any other gate oxide interface, a lot of defects are there, lot of capture zones are there. So they are going to capture, they are going to disturb the flow of the electron, and that is why the mobility will decrease, right? So that these things will happen if you have a surface device when electron is flowing across any surface of interface defects, okay, interface layer between two junctions. Here for MOSFET, it is silicon dioxide, and across this interface my electron is flowing. So that is prone for defects, and electron definitely capture over there. Electron suffers lot of scattering and everything, and mobility has reduced. But here you see the electron is flowing through the bulk, just like a BJT part. Here electron is flowing through the bulk. Advantage is that here the mobility is unaffected. For an example, the mobility of silicon, mobility of electron across the MOSFET, mobility of electrons in the silicon across the MOSFET, like maybe 700, 800 centimeters square per volt second, right? Because it's not at all close to 1000, because my bulk mobility of silicon, bulk mobility of electron across the silicon may be 1000 or 1100, 1200 centimeters square per volt second. The moment it goes to the interface layer, interface of any like silicon dioxide interface, it will reduce to 700, 600, just approximately half. Okay, but here you see the electron is flowing across the bulk. So that means here the electron mobility of, if you take gallium arsenide, which is nothing but 8500 centimeters per volt second, which is really high. So here my electron mobility is not at all affected by defects or interface charges, right? So it is that whatever gallium arsenide defects, whatever the gallium arsenide mobility you have considered, you can put it over there. That means the mobility here 8,500 centimeters per second, and it is not at all reduced mobility. Okay, so this is the one advantage that you are going to have over here. What's about my capacitor? So here mobility is very, very high. That is actually our discussion. We end up with mobility is high. If you are taking, okay, if you are taking gallium arsenide, it's further high. Okay. What's about my capacitor? Capacitor for MOSFET, if you remember, that is actually epsilon by Tox. And what is the epsilon for silicon dioxide? It is 4, and Tox is equal to thickness. Okay. But here this capacitor you are seeing, this capacitor is also epsilon by I can see Hx, right? My H, X or Y? Hy, right? Hy anyhow it is very, very small, like few nanometer only, right? Depletion layer across Hy is very small. But what is this epsilon for gallium arsenide? Well, look at the difference. Here it is 4 and here it is 12. So your CS is also high as compared to the MOSFET. Your CS is also high as compared to the MOSFET. That means your mobility, your transconductance is proportional to mobility. Your transconductor is proportional to C. Both the cases, my mobility is very high. My capacitor is also very high. So definitely my GM is very high. So you can tailor your GM at any particular frequency. Suppose, and for an example, like what I told you, the philosophy is little bit different. You have to see what is your ideal frequency that you can achieve. Suppose you can achieve 800 gigahertz, okay, with this MESFET. It's suppose. Then designing a particular mixer at 200 or 300 gigahertz won't issue, because you can 800 gigahertz, you can step down to 200, 300 by adjusting W by L. See, there is absolutely no issue, right? But yeah, the problem is that other way, like your maximum limit is 200 gigahertz, and if you are supposed to go to 800 gigahertz, it is practically impossible. So this is the beauty of this gallium arsenide. So here people have natural choice is gallium arsenide, because gallium arsenide is giving very, very high mobility, approximately 10 times higher than silicon mobility. So it's a natural choice. Another thing is that this structure, MESFET structure, it has having some added advantage. The carriers are flowing through the bulk. Since the carrier is flowing through the bulk, it is not suffered any kind of collisions. Scattering is very, very low. So mobility is very high. Moreover, the thickness, for capacitor thickness, the thickness of it is nothing but a depletion layer thickness, which is also equally low. So if Tx is low, so what I'm trying to say, if Hy is my low, so if it is 12 is high, 12 is definitely 3 times high, right? So definitely your CS is high, and you'll have a huge operating frequency. So that is one of the great advantage of having GM on this like MESFET structure. And here people are not confident to go for silicon. MESFET structure is fine. It is, so you have a MESFET structure where electron is flowing through the bulk. Now you have a choice. Like you can make MESFET structure for silicon. You can make MESFET structure for gallium arsenide. Definitely you are going to operate. You are going to see high frequency applications. You will be going for gallium arsenide or compound semiconductor who's having high mobility, right? So that is the one. That is the great advantage you will be having on it, right? So that's the things. So I'm stopping over here. So please let me know if you have any doubt. Hello. So it looks like you have any doubt.
No, sir.
No, sir.
Yeah, thank you.